surrounding iron atom, they need to be undergo some deformation. Okay? So there's evidence from an X-ray diffraction shows about that. So, okay, so we talk about the solid solution, two different types of solid solution. And now let's talk about the crystal imperfections or defects, because defects are so important. The reason for that, that's related to the topics of this class. Again, the structure determines the problem. Okay, structure is so important. But defects, any crystal, there's a defect. Okay, there are always defects inside. Many different types of defects. The reason why we have to study the defects is because the defects affect many properties. Okay, many times we prefer those kind of defects. Okay, later on in chapter 6, we will say like a grain boundaries will be preferred. Okay, so as I mentioned to you before, for the mechanical application, you prefer those kind of finer domains. Why that? Because we want to have more grain boundaries. The grain boundaries are the helper. Okay, they help to improve the mechanical property. So we will learn more about that in chapter 6. Okay, so they will affect the mechanical property, but many cases defects will affect the chemical property. Okay, especially for corrosion. Metals, corrosion is a major problem. Okay, for those kind of, once again, if you use grain boundaries, if you put a single crystal copper and a polycrystal copper, polycrystal means you have many domains, there are many grain boundaries. Putting the same etchant solution, you will say the polycrystal domains will be dissolved faster or will be corroded faster. Easy to understand, right? Why? Is it because of grain boundary? Grain boundary, today I'm going to tell you, grain boundaries are more chemically active because they have a higher energy. Easy to understand, right? So, and also they have a different electrical property. Later on, when we talk about the semiconductors, you will say you need to dope. For the pure silicon wafer, it's not a good semiconductor at all. For the real microelectronic application, you have to dope defects inside. Okay, so they will also affect the electrical property. So indeed, when we talk about the defects, imperfections, there are many different types. Depending on their dimensionless, we could have the point defects, those kind of spherical or the point-shaped zero-dimension defects. We could also deal with line defects, so one-dimensional line shape, or sometimes we call them many times we call them dislocations. Today we're going to briefly talk about the dislocations here, and also we could get the two-dimensional defects. So I will also give you all those kind of planar defects. Okay, grain boundary is one type of a very important two-dimensional surface defects. Okay, or we could also have a three-dimensional defect like cracks. Okay, those kind of volumetric cracks, we call them three-dimensional. Okay, so let's talk one by one. If we talk about the zero-dimension defects, we get the vector-6. Easy to understand. If one of the atom could be on the surface, could be inside the single domain, if that one was missing there, many different ways could lead to removal one of the atom from the crystal. Okay, so we call those kind of defects point defects, zero dimension. Okay, so indeed, later on you will see the energy of formation for the vacancy is not that high. 1 electron volt is enough. Okay, remember this number. 1 electron volts, we can actually use this energy of formation to calculate the density of these point defects at a different temperature using what we are going to learn in chapter 5. Yes?
So how can the energy formation be consistent across different materials if they're packed differently and they have different bonds to each other?
Good question. Okay, good question. So the question is, if you think about many different metals, right? So you could think the energy requirement for removing like an atom from the crystal lattice structure could be very different. Why there's a 1 E way, right? That's your kind of like your question. Okay, so the question is because of this. Yes, I agree with you. This number is just a rough number. Okay, it's not for everyone. You know, if the metal has really high lattice energy, this number will be significantly higher. But this is just a rough number. For many of the T metals, they have that number. Okay, but that's still significantly affected by the TM, the melting temperature, and the lattice energy. Yes, but this is a rough number. Later on, we are going to use that number to calculate the Pond defect density at different temperature. Okay, I just want you to remember, this can give you a scale, okay? Indeed, the vacancies, think about that one. You know, the density of a vacancy in some common metals, about 1 per, like 10,000, or could be larger than that, okay? So, but it's roughly in that number. But so that means it's frequent. Think about the three-dimensional packing of atoms. 1 out of 10,000 is not a small number. Okay, so that means you will frequently see the Pond vacancies. So therefore, the Pond vacancies, the neighboring Pond vacancies can move together because of the diffusion. What we are going to talk about that in chapter 5. Okay? So when some of the neighboring Pond defects connected together, they could form like a line defects. Or if there's a lot of these Pond defects accumulate to a small volume, you could get like a three-dimensional void there, right? So easy to understand. So they can be clustered. The thing I want to mention here, the Pond defects can be clustered. And the reason why there are many of those kind of Pond defects in the real metals, one related very important mechanism for the formation of these Pond defects is because of plastic deformation. This one I'm going to talk about that in a very detailed, you know, give you a lot of details in chapter 6. So that means plastic deformation means once the deformation occurs, it will not go back to their original state. This against the elastic deformation. Elastic deformation means once the deformation occurs, it will go back. Okay, so, but don't worry about that. For plastic deformation, we are going to talk much more in chapter 6. And also, the rapid cooling, you know, if you have a metal, if you let that cooling down very fast, that means the the outer cooling temperature, delta T, is very large. Some of the atoms will not have enough energy to move to their energy favorable crystal lattice structure, right? Or to the lattice pond. So therefore, some of the meson size that are not filled by the atom that will generate Pond defects. Okay, and also, especially, you know, when the metals are bombarded by like a gamma ray or those kind of a high energy, you know, subparticles, they could also remove because there's a lot of energy momentum transfer from the high energy subatoms to this atom. They could also remove the particle bombardment is not that common, okay, in the real world applications. So indeed, in addition to these kind of traditional vacancies, another type of vacancy could also occur. We call that that could also occur during kind of like in the interstitials between the single crystal domains. Okay, so in that case, once again, this does not occur naturally. Usually that's under the high energy irradiation, like a gamma ray or sometimes actually could also generate these effects. So what happens here is some of the atoms underneath the high energy bombardment, they will change the shape and then they will be squeezed into the interstitials. So in that case, this kind of a deformed atom, you can also think them as a type of vacancies. So that's related, here is a general defect, okay, generated by this irradiation process. When we talk about ionic crystals, there could be two other type of defects. One is, we call that the Schottky imperfection. So that means, don't forget, when we talk about ionic crystal, like sodium chloride, okay, you need to keep the overall crystal electrical neutral, right? So in that case, if there's one in this case, could be a cation that was removed by some way. Could be irradiation, could be other way. Then to keep the regions electrical neutral, another anion needs also to be removed. Otherwise, you cannot keep the electrical neutral, right? So this kind of, both the remote a pair of anion and a cation to keep the electrical neutrality, we call that the Schottky imperfection. Or another way could, when we talk about the ionic crystal, some of the cation could be, when they're small enough, they can move toward another interstitial site. They form these kind of pairs of cation. That could also happen, though energetically it's not preferred because there's a lot of repulsion between them. But that could also happen. In that case, we call that the Frankel imperfection. That also occurs in the ionic crystals. Okay. So and one thing I want to mention: if you have some low level of impurity atoms, okay. So later on we will talk about that, especially for semiconductors. When we dope like a phosphor atoms, very low level, okay, perhaps 1 out of 1 million silicon atoms, there's 1 phosphor atom there. For those kind of impurity atoms, we could also think them as a Pauli defects. Okay, so now let's move to the secondary or the two-dimensional defects. We call them line defects, or we can also call them dislocations. So indeed, for the line defects formation, line defects also widely present in most of the crystals. Okay, so later I will show you one example here. This is an electron microscope image of iron. Okay, this is the iron. So you see these kind of dark points, those corresponding to the line defects. It forms lines. Okay. So these kind of dark lines. The reason why they generate these lines is because when we collect the SEM image, you use the electron as a probe. Okay, you want to see what happens on the surface when the electrons are reflected. When they see these kind of defect sites, the reflection of the electron will be different than those of the single crystal domains. So therefore, in the final stage, you will see a dark line. So that's related to the line defects. As I mentioned, the line defects are also very common. There's a lot of line defects. From that one, you can see the density, right? It's really high density. Line defects. The line defects are formed, also many processes involved with the line defect formation. Solidification, some regions are cooling down very fast. And some other, some neighboring regions may not be that fast that could generate these kind of line defects. And also, if the metals undergo a deformation, we call that a permanent deformation or plastic deformation. For that one, see, for example, when you apply a high pressure, there could be a crystal plane movement. Okay, some parts will be moved against another. That could also generate line defects. Okay, that one. Especially for the SEM, as I showed you, for those, iron, actually, because during the fabrication process, they undergo like rolling and many other, mechanical treatment. That will introduce a lot of, deformation. So that will also generate the line defects. And the vacancy, as I mentioned, if you have a significant amount of vacancy, they will diffuse. Okay, they were joining with each other. They could also form lines. The line defect could also, caused by the cluster of vacancies. And also for the line defects, there are 2 major types. One is called the edge dislocation, edge line defects. Another one is related to the crystal plane rotation. We call that screw dislocation. I will briefly talk about that. But indeed, in most of the crystals, you will see both. Okay? Or we call that mixed dislocation. So that means mixed dislocation has both the edge dislocation and also the screw dislocation. The edge dislocation is very easy to understand. Okay? Think about that one. If you think about a perfect crystal, under some of the deformation process, some of the crystal planes will be shifted against each other. Okay, in that case, see for example, originally you have this line, you should have this line, right? If it's repeated in 3D periodicity. But indeed, because under some deformation process, some of the lines were missing. In that case, if you compare the density here and the density above, they are different. Between them, there is a translocation, kind of like transition area. Those areas will have the line defects. Okay, so that means when you have an extra half plane, in this case, these regions have an extra half plane compared to the bottom ones. For those, you will see edge dislocation. Okay, but actually, to define the edge location, we can use a Burgers vector or sleep vector, but that's too much. Okay, I don't want to talk much about that one. But the thing is, these edge defects is because of the missing of a half plane. Okay, so they will generate internal stress because of that. In addition to the edge dislocations, which is more like a kind of like a parallel to the surface. There's another way related to the line formation, the line defect formation is if you have a perfect plane, if you imagine about that one. If there's a surface being inserted into that, and then we twist the crystal. One is up, one is down. You will generate these kind of defects, right? So indeed, between these two lines, you will see this kind of interfacial area. Those areas will also represent a line defects because you will see a dark line under the SEM. So that one is because of kind of like a shear, right? And so when you're applying a shear force to the crystal, when they twist it a little bit, so we call that screw dislocation. Okay, so once again, we can use these kind of Burger vectors to represent that. So this one is parallel to the dislocation line, but that's too much. So I just want you to know about that one. Okay, so there's two ways for generating line defects. One is twisting. One is more like on the plane. So okay, so as I mentioned, in most cases, when we talk about the two-dimensional line defects, we will not see the single one. We will see the both. See, for example, what here? Here you will see the screw dislocation when it's coming out because there's a defect there. There's a stress being built up there. Usually, to reduce the overall energy of the crystal, you have to another paired location. That location usually, see for example here, this one shows the edge dislocation. Okay, so when they pair it together, they will slightly reduce the overall energy. They will release the internal stress. Okay, so in many cases you will see both type of line defect there. Okay, so as I mentioned, we can see the dark lines in the SEM because they have a different electron density there. So they will reflect differently. Okay, when we talk about the two-dimensional defects or the planar defect, you can think about their planes. Okay, one very important one, the plane defects, you can think about the grain boundaries. Okay, but grain boundaries, if you think about the grain boundaries, when you see that, if you see the grain boundaries from this kind of optical image, you see the lines, okay, but don't be confused. They are not a two-dimensional, they are not a single dimension, they are not a line defect, they are surfaces. Right? Think about that. You have a three-dimensional grain. They are separated with the neighboring grain by the grain boundary. Grain boundary are not line, grain boundary are the surfaces. Right? So therefore they are two-dimensional. Grain boundaries are two-dimensional. See, for example, if you think about the center grain with that grain, here is the interface area. Those are the grain boundaries. Okay, so that's important. Grain boundaries is the most important one. Twins, I'm going to talk about that one briefly in chapter 6. Those are also commonly the planar defects, or there could also be related to the twisting. I will briefly talk about that one, or the low triangle boundaries.